let's talk a little bit about a sampling distribution. Before we do that, let's review some terms that we learned at the beginning of this semester. We know that a population is a set of measurements. This can be either existing or conceptual. However, a sample then is a subset of the measurements from this population. We have two numerical descriptive measures we can talk about. One is a parameter, which is a numerical descriptive measure of a population. This can be mu, the population mean, sigma, the population standard deviation, sigma squared, the population variance, or p, the population proportion. And these are all fixed quantities. Now we can also have a statistic, which is a numerical descriptive measure of a sample. X bar being a sample mean, S, the sample standard deviation, S squared, the sample variance, or P hat, the sample proportion. Of course, these quantities may vary because we could have different samples giving us different values for these. So it's important to know that these statistics are used to make corresponding inferences about our population parameters. We can do this by estimating a population parameter using the statistic. We can do this where we make a decision about the population parameter. This is called hypothesis testing, which we'll do, or making predictions, and this is called regression. So we're going to do this as all part of what's called inferential statistics, and it's really the power behind statistics. So in order to do this estimation, hypothesis testing, and regression, we need to know a little bit about a sampling distribution. A sampling distribution is a probability distribution for our sample statistic that we're using. So let's give a quick, just brief example here. Let's say we had some of our students in our class went fishing, okay? Let's say that Emily went fishing down at Grand Lake St. Mary's and she caught 5 fish. And let's say the fish is randomly distributed. We'll just say X is the length of the fish, okay? Okay, Emily catches 5 fish of length 7 inches, 12 inches, 4 inches, 11 inches, and 10 inches. Okay, let's say Robert catches some fish of 5 inches, 11 inches, 13 inches, 12 inches, and 9 inches. And let's say Albert also goes fishing and catches 4 inches, 8 inches, 9 inches, 11 inches, and 15 inches. All right, we'll stop there. Okay, so let's say I ask these students to calculate, calculate the average length of fish that you caught. So we can calculate X bar, which is the average length that Emily catches, right? So Emily, how would you do that? You would take and add up your 5 fish, right? The lengths of your 5 fish. Divide by 5 or use your calculator. Let's say Emily gets the average length of 8.8 inches. Let's say I ask Robert to do the same thing. Go ahead, Robert. Figure out the length of fish, your average length of fish that you caught. And the average length of the fish that Robert caught is 10 inches. And let's say we do the same thing for Albert. Go ahead, Albert. I wish you guys could talk back and tell me. Just kidding. His length was 9.4 inches. All right. So one thing you want to think about is the distribution of your underlying fish. This is X is the length of fish. So all the fish, let's say we'll use Grand Lake St. Mary's. This is all, if we measured all of them, they would have a certain average and a standard deviation, okay? One thing is we can assume that that's normally distributed, but we'll talk about that here in a second. And then we have a different set of data. The different set of data is all these sampling means. So if I took all possible samples of size 5 out of Grand Lake St. Mary's, this isn't all of them, but just say we did all possible samples we could, and we calculated all of the sample means for all possible samples. This would be our sampling distribution, okay? The sampling distribution of the sample means. It's just all these averages. Are you with me? So what the sampling distribution tells us is we can calculate the population mean of all of these means. That's called the mean of the means. Okay? Now let's look at what the central limit theorem tells us about this distribution. Okay, the central limit theorem tells us that the x-bar distribution, which is this distribution of all the x-bars, is a normal distribution. Okay, two things have to happen: is the underlying distribution of x is normal, or our sample sizes are larger than 30. Okay, so if I made the assumption that the sample size, the length of the fish is normally distributed with mu and sigma, then this is also going to be a normal distribution. And that the mean of this distribution, mu of x bar, is going to be equal to mu. Remember, that's the mean of the means. So these means are going to be equal. And that the standard deviation of the x bar distribution, sigma x bar, is going to be the standard deviation of our underlying distribution divided by the square root of n.